Hello and welcome. This is SFU Math 232. My name's Brenda. So we're now looking at section 6.1, seeing matrices as transformations. So we're going to introduce yet more vocabulary. So let's just make sure that we have the idea of a function, and possibly we're going to have some more vocabulary than we have had surrounding this before. So the idea is a function is something like a computer program. It could be like a cash register. It can be an algebraic statement. It can be a lot of things actually. And what happens is you put in an input into the function and you get it out an output. Okay, so the idea is that you've got your function. There it is, some sort of a function. And the idea is here you have on this side a domain, and that is the set of all possible inputs. So you have a set here of all possible inputs that can go into your function. And then what comes out here is the range. That's the set of all the outputs. So that is the set of all the outputs. Sometimes also, if we have a larger size object over here on the output side than what is actually the range, we will call that the codomain. So the codomain is any set containing the range. Okay, so effectively what it is like this. There's more stuff like that. And this outer one here is the codomain. Okay. It's also possible that when we're thinking about a single input, we could have what we would call here a single input X, and then we have a single output Y. We sometimes will call the single input here X, and then we might call here what's coming out, not the output. So sometimes, okay, let us just put here, sometimes, instead of drawing extra arrows, sometimes we would say, for example, call this the input, single input, and then call this the output. Sometimes we will call this the image, the output. This would be the image of X. And then we would, at that point, call this here the pre-image. That would be the pre-image of the output Y, or this guy here could be the image of the input X. Okay, so we write Y equals f of X. We write Y equals the value of f at X. We write Y is equal to the image of X under F. And we can also write F maps X into Y, or f of X. There's a whole bunch of vocabulary and notation surrounding this. Sometimes we can even do this: X maps to f of X, or X maps to Y. That's telling you the function there. Okay, so there's a bunch of ways, but the idea is that we have a set of possible inputs, and then we have a set of possible outputs. Okay, now we're going to broaden this a little bit and introduce the idea of a transformation. So if the function has inputs and outputs which are vectors, then we're going to call the function a transformation. We often use capital letters for that to name the transformations, and T is in fact a very common letter to use, just like F is a common letter to use for a function. It doesn't have to be, of course, but that is sort of a standard. So if the transformation T maps vector V to W, then we can use that same type of function notation. The vector W is V under the transformation T. Now we might even write it like this: T transforms V into W. Okay. So we have an added wrinkle here over the regular function discussion, and that is that v and w could be in different dimensions. So for example, the input could be in Rn and the output could be in Rm. Okay, so if we have the case where the dimension of the input and the output are the same, then we call the transformation an operator. That's where that word is coming in. Is a transformation that maps, like say for example, R2 onto R2. That would be an operator. A transformation that maps R3 to R3 would also be an operator. So that's when the dimensions are the same. Okay, let's just take an example here. So we've got T1 be the operator on R2. So that means it's going to have to go from R2 to R2. That multiplies the first component by 2 and the second component by 1/2. So what does that look like? Well, T1 takes an input, x1 and x2. That's the vector x. And it does the following. It produces an output where the first component, that is x1, gets multiplied by 2, and the second component, which is x2, gets multiplied by 1/2. So there is the transformation T1. We could also write that like this. T takes the vector x1, x2. The vector x1, x2 is mapped via T1 to the vector 2x1, 1/2 x2. Okay. If we set up two vectors, for example, if we set up the vector v being 1, 3, like that, then we could say T of v is equal to w. And in this case, w would be 2 times the first component and 1/2 times the second component. Okay. It's an operator. The dimensions are the same. It's also a transformation. Okay, so here we have the next example. T2 is going to be a transformation on R3 that maps to R2. So it's not an operator, but it is still a transformation. Okay, so the input, in this case, the input is a vector in R3. That looks like this. There's a vector in R3. And our output will look like this. It will be a vector in R2, and what does it happen? Cubes the first two components. Leaves and doesn't do anything to the third component, produces something in R2. Okay, so we could then write our transformation like this. Our transformation x1, x2, x3 looks like this. x1 cubed, x2 cubed. Okay. Again, we could write it like this, x1, x2, x3, and then we could say is mapped via the transformation, oh, this is going to be called T2, via the transformation T2 to, there it is. Okay, can we represent this one as a matrix? That's a question. Can we represent T1 or T2 by a matrix? And so we'll have to think about these sort of things. So in this case, we have T2. T2 is such that it maps R3 to R2. Okay, your shadow is actually something like that. You're a three-dimensional thing, and there is a transformation that maps you to your unique shadow, which is two-dimensional. You see it on the ground. It's not this transformation, so that's a type of projection. And that takes a three-dimensional object and maps it to a two-dimensional shadow. Okay, how about what if a transformation is encoded in a matrix? So we have a matrix here, a 3x2 matrix, and we're going to let T3 be the transformation that maps a vector in R2 to the vector AX in R3. Okay, so we have here a 2x3 matrix, that is A, and we are going to multiply that by a vector, which is going to have to be of size 3 by 1 because these inner dimensions have to match, and it's a vector, so that's going to be 1. So we can see that the output is going, this is x, so you can see what the output is going to be. It is going to be a 2 by 1. That is a vector in R2. Okay, so that is where we're here. vector. Oh, sorry, I did this actually backwards. Let me fix this. Sorry. I was like, why is this not working? This is not a 2 by 3 matrix. It's a 3 by 2 matrix. So let's try that again. So A is a 3 by 2 matrix, and our vector X then has to be a 2 by 1 because these still the inner dimensions have to match. So we have here A, and then we have something here that's in R2, and then the inner dimensions match, and then we get the outer dimensions here, which is 3 by 1. That is in R3. That is the way I meant to do it. Okay, so that is the transformation T3. So let's look at what that is. I'm going to take the matrix A there. That is 3 minus 1, 2, 2, 1, 5. And I'll multiply it by a vector in R2, and then I get this thing, the output vector. It looks like this: 3x1 minus x2, 2x1 plus 2x2, and x1 plus 5x2. Okay, so what do we have here? We have x being mapped via T3 to y. This one is in R2, and this one is in R3. So we can write that in this way: T sub A, the transformation defined by the matrix A. It operates on the vector x1, x2, and it produces an output vector that looks like this. So this here is a matrix transformation. Okay, so in this case, the domain of our transformation, this domain is all of R2. That is our possible inputs. Domain is all of R2. And then the codomain is R3. Okay, we don't know without further analysis whether the range is actually all of R3, because there may be some vectors in R3 we don't get to via this transformation. But certainly all of the outputs that we do get will be in R3. So the codomain is R3. All right, so that is a matrix transformation, and we have the same exact condition. If A is a square matrix, which will be the case many of the times, then both the inputs and outputs are of the same dimension, and our transformation, our matrix transformation, is then called a matrix operator. Okay, so let's just take a look at this. What is the matrix transformation T, and then that sub 0 m by n? I mean, that is a zero matrix, which is of dimension n rows and n columns. That looks like this, basically all zeros everywhere. Okay, zeros, where there are m rows here, and there's n columns here. That's what it looks like. And so if we take T like that, and we operate on X via that, we will take that matrix of all zeros, there it is, and we will operate on it, and this thing here will be of dimension n, because there are n columns in the this matrix. There are n columns, so this vector here will have, this number here will be an n, that will be the n, and when we get the output here, it will be all zeros like that, and this will be of dimension m. So every vector in Rn is mapped to the zero vector in Rm. So this matrix transformation here is, unsurprisingly, called the zero transformation. Okay, so then we have a similarly straightforward transformation, which we have labeled here T sub in. That is for the n by n identity matrix. So T in of x is going to be in multiplied by x, and this will be in Rn. Because this is an n by n identity matrix. And so what will happen is out here you will get the vector x1 to xn like that, which is exactly this input here. So x is mapped to itself. Okay, that means that we call T sub I the identity operator. Doesn't do anything. That is playing, so I want you to just compare. So compare that, compare to 1 in our normal, in sort of in arithmetic, right? Think of what happens so compare to 1 with multiplication, the operator of multiplying. Okay, if I take x times 1, I get x. So x is the multiplicative identity, and I is playing that same role here. I is the identity transformation. Okay, so now if we have a matrix and we can look again at the problem of solving the system of linear equations ax equals b, and we can view that geometrically as the problem of find all the vectors in Rn, all these guys in Rn, that are mapped by the transformation defined by that matrix to the vector b. This is just it's a fancier way of saying what we've said before. So if we have the matrix A, we could ask the question, find the input vectors, if any, for which T sub A of x is 4, 3, 2. So we want this T sub A, the transformation defined by that matrix A, operating on x will give us the vector 4, 3, 2. Okay, first let's look at what's happening here. This is a transformation that takes vectors, input vectors. What are the dimension of my input vectors? Those are in R2. Yeah, those are in R2. And what will my output vector be? My output vector will be in R3. Okay, you can see that B is in R3. Okay, so what I do then is this is the same as asking this question. 3 minus 1, which we've answered many times before. I'm going to go through one of them in detail and then leave the other one for you to look at yourself, just supplying you with some of the steps. Say we're asking this is going to be this. Okay, so we're looking for two-dimensional vectors x1 and x2 that when I multiply by A, I get the three-dimensional vector 4, 3, 2. So we have in the past, and we will do so now, that is write this like this, like that. And then we will row reduce and figure out what values of x1 and x2 that is. So I first swapped the first and third row. And then I made these two guys to a 0. Okay, then I noticed that row 2 and 3 are multiples of one another. So I can immediately then go to here, dividing through by minus 8. And then this one will be all zeros. Okay, it's a multiple of the one above. Okay, I'm done. That now tells me what is x1 and x2. So I find that the solution vector here, x is x2 is 1/8, and x1 is 2 minus 5 times 1/8, which is 5. Let's see, the 16 minus 5, that's 11. Okay, so there. Okay, so there is a single vector, which is, when operated on by the matrix A, gives me the vector 4, 3, 2. Okay, the second question is the same question, but of course the augmented matrix looks different. There's A is the same, the coefficient matrix is the same, and then the B is different, looks like that. You confirm that I did this right. You go through the steps of the row reduction, and I got to here. Okay, so then when I got to here, I saw this, and there's no way that that can happen. Okay, that is inconsistent. I can see right there that it's inconsistent. I can't have that minus 8 x2 is minus 7, and at the same time minus 16 x2 is minus 16. That will not happen. Okay, so that means there's no vector. There is no vector. There is no vector x in R2 for which the transformation defined by the matrix A operating on a vector will produce this. That won't happen. So there, 2, 5, 6 does not have a preimage. Okay, so now key point. Linear transformation. What does it mean to be linear? A transformation is called linear if it satisfies these two conditions. Okay, this you must be able to extract out of your head at any time, right? That if you take the transformation and operate it on a scalar constant times a vector, it's the same as the scalar constant times the transformation operated on the vector. If you operate on the sum of two vectors, that is the same as the sum of the independent operations on x and y. It's linear. It's linear if these two conditions are satisfied. And then if the dimensions are the same, then we do the same idea. We call it then a linear operator. Call it a linear operator. Okay, I want to point something out right now, a little bit tangential here, and that is, let us consider this function here. Okay, in the way that we're speaking of here, this is not a linear function. Okay, because why? Let us look what happens if I take f of x plus y. That's going to look like this: a times x plus y plus b, which is ax plus ay plus b. What if I take f of x, that is ax plus b, I take f of y, that is ay plus b, then I take f of x plus f of y, I get ax plus b plus ax plus, ay plus b. I get a times x plus y plus 2b. Okay, we see the problem. The problem is f of x plus y is equal to this, whereas f of x plus y is equal to this, and they are not the same. Okay. So this function is not linear. It is a line when we draw it, but the line does not go through the origin. And in the definition here of a linear transformation, this does not fit the definition. You will see, perhaps later, but at other times, you will see that this is what's called an affine transformation. Okay, so we're going to be cautious about that. Okay, so we can see then, by combining these two ideas, that a linear transformation, if you operate on a linear combination of vectors, that you get, you can separate everything out all nicely. So that is the same as operating on each one of the vectors independently, then multiplying by those scalar constants, and then adding. So we're going to ask, of all the transformations we saw earlier, which one of them are linear? So let us take a look at T1 of x1, x2. which was defined in this manner, 2x1 plus and a half x2. And it multiplied the first component by 2 and multiplied the second component by a half. Okay, so then what we can do is, if we want to check for the linearity, we have here t1 of x. We know what it does. And then we would check t1 of kx1, kx2. And that would equal to, we would compute that. That would be 2kx1 1 half kx2. Okay, and then we can compute, that is t1 of kx, and then is that equal, does that equal k times t1 of x? Okay, let's see what t that is. That is 2kx1 1 half kx2. Okay, and multiply the k onto both of them. So maybe I want to even try to be more obvious. It's k times 2x1 times a half x2, and then I multiply the k in, 2kx1 1 half kx2, and I see that that is equal to that. So that I see that k times this is equal to this one here. That is that linearity condition 1. Then I could check the next one. I've got t1 of x equal to like this, 2x1 1 half x2. I could write it like that. And then I have t1 of y, and that's equal to 2y1 plus 1 half y2. Then I could ask, what is t of x plus y? And then I could compare that with t of x plus t of y. Make sure that they're equal. They should be equal. So you check that. They are. This is a linear transformation. So this, therefore, t1 is linear after you check that. Okay, that's the first one. Okay, so that's t1. So let's take a look at t2. t2 of x1, x2, x3 was defined this way. Cube the first two components, lose the third component. This is not linear. I mean, I mean, you can see a cube there. It's clearly not going to be linear. But I mean, what you could do is confirm this. T2 of kx is not equal to k of t of x. Okay, so confirm that by just doing the algebra there. Okay, so this one is not linear. Okay, and then our third transformation, T3. T3 was the matrix transformation, and where we had the matrix A defined in this manner here, 3 minus 1, 2, 2, 1, 5. So this, as we're going to see, this is linear. This is linear, and all transformations defined by matrices are linear. Okay, so why don't you go ahead and check that? Check the check the conditions. Check the two conditions. Check that TA of x is check this. Check TA of x plus y. So get two vectors, x and y. Compute TA of x plus y, and then confirm that that is the same as TA of x plus TA of y, which when I did this, I got this thing here, 3x1 minus x2 plus 3y1 minus y2, 2x1 plus 2x2 plus 2y1 plus 2y2, x plus x1 plus 5x2 plus y1 plus 5y2. So you check that one, and then you can check this. Okay, it's a really good idea to stop the video and do that. Okay, so those are the two conditions that you check. And if they both pass, the thing is linear. matrix transformations are linear. Okay, so given that definition of what it means to be linear, we also then have these conditions here. These just follow directly from the definition of what it means to be linear. That is that the transformation applied to the zero vector gives you the zero vector. The transformation applied to minus a vector gives you minus the transformation applied to the vector. That's k equals -1. And then this is a combination of the sum 1 plus a constant of -1. So those just follow directly. Okay. This is a sort of a recap of what we just said about the affine transformation above, and putting the in maybe function notation that we're more used to. But here we have an operator from Rn to Rn, and we're asking is Tx, where it's defined to be x plus v, where v is a non-zero vector, is that a linear transformation? So we would proceed to start to check, and we would say, okay, let's calculate out what is t times t of k of x, and that's going to be, well, I know what the definition is. It says take your input and add v to it. So here's going to be the output. There, that's the output. Okay, then I will compute that, and that is just going to be take your input, add v to it. And then I will see what this looks like. That looks like this. Okay, then I want to know, are these things equal? Does this equal this? No, it doesn't. No, not equal. Not equal. Therefore, this is not a linear transformation. So we're not allowing that the b in the, if you want to look at it that way, in this ax plus b, this guy, the b has to be 0. Otherwise, it's not going to be linear. Okay, here's a key theorem. Every linear transformation is a matrix transformation for some matrix A. Or so all matrices represent linear transformations. And what's nice about this is that if we have a linear transformation, we can figure out what the matrix is by applying the transformation to the standard, to the basis vectors, and then representing, and then forming A with the as the columns of A as the transformation applied to the standard basis vectors. That is what we call the standard matrix for the transformation. Okay, so we're going to attempt that feat with T1 from earlier as we're going to try to reformulate T1 as a matrix transformation. So here's the definition of T1 again. This is what T1 is. It is x1, x2. It doubles the first one, and it halves the second one. So what we'll do is we'll recall the our standard basis vectors. That's going to be 1, 0, and 0, 1. That's in R2. We are in R2. And so then I compute T1 of E1. So that is T1 of 1, 0, like that. And what happens when I do that? I get this vector 2, 0. Double the first one and halve the second one. And I calculate T2 of E2. I double the first one. I halve the second one. Okay, E2 is 0, 1. So then I write the matrix for this standard matrix for this transformation looks like this. Okay, this column here is this guy here. This column here is this guy here. This is the standard. Standard matrix for T. Okay, and let's just apply that to a vector. See what's happening here. Ax There it is, 2, 0, 0, 1 half. If I multiply it by any vector x2, I will get here 2x1 and 1 half x2. I double the first component and I have the second component. Okay, this is a direct result, of course, that x1, x2 can be written as a linear combination of the standard basis vectors like that. Okay, so now we're going to take what we've been doing and see how we can then set up matrices to do certain types of transformations that we want. So we're going to start that by figuring out what the standard matrix is to do rotations in R2. So we're going to let T be a transformation such that you map vectors from R2 to R2 that rotates the vector about the origin by an angle phi. Okay, so how do we, I mean, the answer is supplied here. How do you come up with that? So what we're going to do to get that standard matrix is we're going to see what happens. So before I answer the question that's here, let us just first take a look how you come up with that transformation matrix, this one here. First we take the vector E1 and we rotate it by an amount phi. And then we ask, where is that vector? Okay, and so then we can just drop down this thing here. We can see, oh, this vector here is the vector cosine phi sine phi, right? Because this length here is 1. It's a rotation of E1. So this is this vector right here, which I've identified as cos phi sine phi, is E1 rotated by phi. Then I look at the same thing for E2. I draw E2. I rotate E2 by phi. And there is E2 rotated by phi. So this is E2, the second basis vector in R2. We rotate it by phi, and we see where does it go, and we identify this point right here and such this vector as minus sine phi cosine phi. So that this one here that I've identified by minus sine phi cos phi, that is E2 rotated by phi. Okay, then I take the results of those two things and I form R phi. So I go here. What is the transformation, the rotation on E1? That's one column. And then what is the transformation on E2? Okay, and then when I do that, I get the transformation rotating by phi on E1 gives me cos phi sine phi, and the transformation operating on E2 gives me minus sine phi cos phi. There we go. Now I have this matrix here. Now I can, for any value of phi and for any vector x, I can simply say, oh, I want to rotate by, well, in this case, I'm going to do pi by 3. I want to rotate by minus pi by 3. Then I put phi equals minus pi by 3. I want to rotate this particular vector. I multiply the r minus pi by 3 by x, and it does this operation for me. Okay, so minus pi by 3 is minus 60 degrees. So let us first just put what is r of minus pi by 3. So that is r of phi when phi is minus pi by 3. That is going to be, you simply fill this in. Cos minus pi by 3 minus sine minus pi by 3, sine minus pi by 3, and cosine minus pi by 3. Okay, all right, so I can make those calculations, and I get this matrix here: 1/2 root 3 over 2 minus root 3 over 2 and 1/2. Okay, now I can take any vector, and if I want to rotate it by minus pi by 3, I simply multiply the vector. I multiply on the left by this matrix. Okay, so let's do that. R minus pi by 3 multiplied by x is going to be this here. 1/2 root 3 over 2 minus root 3 over 2, 1/2. Multiply it by 1, 2. And I get this vector here, 2.23 and 0.133. Okay. All right, so let us just look geometrically what has happened here. I'm here. I started with a vector 1, 2, so it was here. It rotated by minus 60 degrees, or minus pi by 3, and it then where does it end up? It ended up here, 2.23. That's right about here, and just a little bit above. So it rotated down. It's the same length, and it's there. Okay, so. Yeah, so I know that this distance right here is now 60 degrees. Okay. So now what we could do once we have this matrix formed, any vector we want to rotate by minus pi by 3, we simply take that vector and multiply it by this matrix. So this matrix is this one here. This matrix is the matrix that when you operate on a vector, it rotates it by minus pi by 3. And we, in fact, of course, have the general case here. I mean, we could use any value of phi that we want here. We can rotate any vector by any angle simply by doing this operation here. So we have the general case sitting here. Okay, we can do another type of linear transformation, a reflection. So we can let T be instead the transformation that reflects each vector x about a line through the origin that has an angle of phi with the positive x-axis. Okay, so we do exactly the same thing. We form the images of the standard unit vectors, and then we make the standard matrix. In this case, we typically denote that by h of phi, and we have it there. So let's just again quickly draw what that looks like, what we're doing here. We can see what's happening. We have our axes, and we have a line which is at an angle phi. There it is, that angle right there is phi from the x-axis. Now what we want to do is take vectors and we want to reflect them across that line. So what we do is we take E1 and we reflect it across the line. So this angle is also going to be phi. Then we ask what are the x and y components of this vector. Now this one here, E1, this is E1 reflected across this line right here. Okay, then we do the same thing for E2. We take E2, there it is, and we reflect it across the line. And then that is going to end up, we have to come here, and then the equivalent distance there, like that. So it's going to be somewhere looking right about down here, like that. And we figure out what the x and y components are of this guy here. What are the x and y components here of this guy, which is E2 reflected about this guy here. Okay, we put those two things together and we find the transformation matrix that allows us to reflect any vector across a line which is an angle phi from the x-axis. I highly encourage you now to just work through the details, see where these things are coming from, and then the trig identities that allow you to get to here. Okay, so now let's take a look. What does it mean? What would the matrix be for reflection about the y-axis? Reflection about the y-axis. So that it would be h pi by 2. And that would be cosine of pi, sine of pi, and minus cosine of pi. So we get that thing there. So what I claim is that if I take a vector, I multiply it by that, I will get a reflection across the y-axis. Let's just take a look. What happens if I take h pi by 2 and I multiply it by the vector 1, 1? What will happen? Well, I'll do that multiplication. That will look like this. I'll multiply by 1, 1, and I get the vector minus 1, 1. What does that look like? Let's see. We started with 1, 1 right here. 1, 1. And then we ended up with minus 1, 1, which is right here. Minus 1, 1. Okay, so it reflected it about the y-axis. We reflected across here, reflected about the y-axis. Okay, if I wanted to do a reflection about the x-axis, then the angle is 0. Reflection about the x-axis. We have h of 0. That will be this guy here. 1, 0, 0, minus 1. And then I can take some vector. I don't know, let's just pick one here. Minus 1, 1. How about that? Minus 1, 1. And I will then take that vector, minus 1, 1, and I will multiply on the left by this matrix. Minus 1, 1. And what will I get? Let's see, I will get minus 1 and minus 1. That is right here. Minus 1, minus 1. So I got reflection across the x-axis. So now with this matrix in hand, I can figure out how to reflect across any line. So we had the rotation, the reflection, and the final one we're going to take a look at is the projection. Okay, so that we're going to call this an orthogonal projection. It maps the vector x onto a line through the origin that has an angle phi with the positive axis by dropping a perpendicular to that line. This one's also a linear operator. Let's just make sure that we understand what this is, and then we can see how this works. So let us just first note that what does it mean, orthogonal projection? And so let us just take a look at what it means, orthogonal projection onto the x-axis. Okay, so you have some vector. You have some vector. Here it is. And you are going to project it orthogonally onto the x-axis. It means you can imagine a light source up here shining down, and you can ask, what is the shadow of, you notice these my light source here is orthogonal to the x-axis. So I'm going to ask, what is the shadow of V on the x-axis? And so that shadow is going to be this guy right here. So I project this down like this, orthogonal. That's what it looks like. Okay, so if that's the orthogonal projection onto the x-axis. If I want to do it onto the y-axis, I imagine a light source here shining in this direction here like that, and I project it this way. That's the shadow over here. So I get this guy right here. So that's the orthogonal projection onto the y-axis. The blue one is the orthogonal projection onto the x-axis. I don't have to just do these on the axes. I, of course, can do it onto any line. Okay, so here, how is this coming up here? How does this come up? Which is what is going to allow us to get the matrix that we need, because we already know what this guy is from the previous example. We know what this guy is. So this series of steps right here is allowing us to get this, and then this here will allow us to get the matrix that we need. Okay. So let us just take a quick look at how that comes about, how you see that. You draw like this, and you imagine some line. There it is. It's the line, and it is at an angle phi from the x-axis. So now we want to project onto this line. So we imagine a vector, v. I called it x actually. Let's imagine a vector x, like that. There it is, x. We want to project that orthogonally onto the line. So we imagine a light source over here, shining light in this direction here, orthogonal to the line. So that means we're going to get the projection right here, like this, like that. And our projected vector will be this guy right here. Right here. That is the projection of x onto the line. So this is p phi times x. Okay, now in order to see how this relates to the reflection linear transformation, I'm going to label this guy right here, u. Okay, then you can see that this u here is p phi of x minus x. That's what this is. That's where the u is there on that diagram. Okay, then I imagine just going onto the other side by amount phi. Right there. So that this is also here. This vector is also u. Okay, so now what I've done is I have reflected, this guy right here is the reflection of x across my line, the black line. So this is h phi times x. That one is h phi times x, and then there's u. And so you can see now that x, that is x coming along here, plus 2u is equal to h phi of x. That is getting you this guy here. Then you use the algebra and you come here. And then a little bit more work and you come here. So go through all those steps yourself. Now feel free to ask in our Zoom session if you want me to fill in more details on that. Okay, so now we can figure out what the general matrix is for projection onto a line at angle phi through the origin. Okay, so I'll just write this out in general and then we'll do the example. In general, p phi is equal to cos squared phi, sine phi, cos phi, sine phi, cos phi, and sine squared phi. Okay, that's what happens. So now let's take a look when phi is 0. That is projection onto the x-axis. When phi equals 0, that is projection onto the x-axis. Okay, so what happens? So that is going to be p of 0, and that is going to be 1, 0, 0, 0. Just go like this here, 1, 0, 0, 0. If I multiply that by some vector, x, y, what do I get? I get the vector x, 0. I get what's on the x-axis. I get the projection onto the x-axis. Okay, similarly, when phi is pi by 2, we get projection onto the y-axis. And that matrix looks like this. Okay, we pick up the y component, but we can do it onto any line. And that gives us the ability now to set up matrices that rotate by any angle we want, that reflect across a line of any angle that we want, and that project upon a line at any angle. Okay, that is a lot, and that is section 6.1. I'll be back soon with the next installment. Thanks, guys. Bye.